Pre-calculus students, this is Mr. Hale. Welcome to your 9.2 notes today. We're going to take a look at ellipses and let's get started. So an ellipse is defined as the locus of points in a plane, the sum of whose distances from two distinct points called foci is constant. Now you can see the diagram here to the left. I actually want to show you though on something called Geometer's Sketchpad. I'm going to show you kind of a visual of this. You can see if we had a string connected to 2 points and we drag that pencil around, you can kind of see what that looks like. Kind of cool stuff. Now I'm going to come back to that in just a moment, and we're going to look at that again for a couple of other things. Some terminology we need to know. The major axis is the distance between vertices. The minor axis is the shorter of the two axes. And I should probably point this out. On either side, we don't have these labeled, but at times you'll see these 2 points called co-vertices. So if you ever see the term co-vertices, it's referencing the ends of the minor axis. It's kind of like a squished circle, right? So it's kind of like the shorter radius, the shortest radius is the end of those is where the co-vertices would lie. The center, I think, is self-explanatory. All right, this diagram over here has a lot going on, but the main thing we're trying to point out here is the relationship between A, B, and C. A represents half the major axis. B represents half the minor axis. I think of it as the largest radius and the smallest radius, although I'm misusing those terms a bit. And C represents the distance from the center to the focus point. Now you can see there's a whole bunch of stuff going on here, and you've got some formulas, but let me show you a way that we can think about this that might help you to understand it. The first thing you need to understand is that the string that we're dragging around to create the ellipse has a length of 2a, and you can kind of see it visually if we drag the pencil down to here. You can see that this gap from the focus point to the vertex is actually doubled up, which makes up for that gap right there. So the string has a length of 2a, okay? But now, here's the really cool part. The relationship, since we know the string is 2a, we know this hypotenuse of this triangle right here has to be a, that's half the string. We already defined this as b, the distance from center to a co-vertice, and then c is the center to the focus. So we've got this Pythagorean theorem situation, except, well, it's Pythagorean, but it's a little demented. You can see it here, a squared equals b squared plus c squared. You might also see it written as a squared minus b squared equals c squared. Honestly, any of those are fine. Use what you're comfortable with, and it makes sense. Just make sure you don't accidentally use the real Pythagorean theorem. I mean, we are using Pythagorean, but we have the sides labeled differently. All right, and when we get to hyperbolas, we actually have a little bit different format on those, so we have to stick with this one here. All right, the standard equation, you can see the 2 forms. The first is when you have a horizontal major axis. This is like if you had a circle and you squished it from the top and bottom, so it's wider than it is tall. This second version is a vertical major axis, and that one would be, again, like if you took a circle and then you squeezed it from the sides, kind of squished it, so therefore it's actually taller than it is wide. Now, these 2 standard forms look very, very similar. There's only, as you can see, one difference. It's the location of A and B. So the point is, if the major axis is 2a, then that means the distance, from the center to a vertex is a, and that is always bigger than the distance from the center to a co-vertex. So the point is, if it's horizontal, the bigger number is under x. If it's vertical, the bigger number would be under y. And we'll take a look at that as we move forward. Hey, one more thing we want to talk about. It's a new term for you, eccentricity. We're going to really focus on this. We'll hit it more second semester too, when we go a little more in depth with some of these figures. But eccentricity is defined as C over A. We can use eccentricity to figure out at times what shape are we talking about, but also we can tell, you know, a little more detail about the shapes. We'll get into that later. All right, let's get right into it here. So we're going to, for the next couple of problems, identify the conic as either a circle or ellipse, and then we need to find all the key information, and we'll go ahead and sketch that graph while we're at it. All right, so first thing I want to know, if it's a circle or ellipse, that's actually pretty easy. Those two numbers right there tell the story. This is most definitely an ellipse. If it was a circle, those two numbers would be the same. All right, so let's talk about what we know. I know that this term right here has to be a squared, so that means that a is going to equal 10. This term right here, 36, has to be b squared. And again, the only reason I know which one is a and which one is b is it's based solely on the fact that a is larger than b. So a is 10, b is 6. The center, well, there's no move from the vertex, so we're just at 0, 0. I said the vertex, I meant the origin, of course. And the radius wouldn't apply. We'll deal with foci. We can deal with eccentricity at the end as well. All right, so let's go ahead and sketch this thing. I know the center is, again, at the origin. And when I see this, I look and I'm like, okay, remember, the b value of 6 is horizontal, so that means I need to move 6 spaces right, 6 spaces left. The a value of 10 is a vertical change, so we're going to move up 10 and down 10, and again, in both cases, those are from the center of the shape. And then we're going to go ahead and sketch it. I always find ellipses a little tricky to sketch, so my drawing will not be perfect. That may shock some of you. Not those of you that know me, though. And the thing is, your drawings won't be perfect either, and that's totally fine. You don't have to worry about perfection. We're looking for a nice sketch. All right, we still have a little more work to do. First thing, let's go ahead and list the vertices. We've already graphed them, so that's pretty simple to do. Those were the furthest points from the center, and I'm just going to list them as 0, plus or minus 10. Okay, we also need to find the foci. Well, in order to find the foci, I need to find C. And so remember, we have to use, and I'm going to jump back a slide just to remind you, down here we have to use that alternate version of the Pythagorean theorem. So it's a squared equals b squared plus c squared, or you could just do it as c squared is a squared minus b squared. So that's 100 minus 36, which is 64. That's convenient. C is 8. Okay, one other thing about the foci that we probably mentioned, but we probably wouldn't hurt to highlight that, is the foci are always going to be on the major axis. So I know the foci are at 0 and plus or minus 8. Okay, and then the last thing we need to do is the eccentricity. Remember, eccentricity is C over A. So in this case, that would be 8/10, which of course we could simplify to 4/5. Now, the point of eccentricity, you may be wondering just a little bit, like, what's that even mean? And again, we'll get more in depth with this later in the year, but for now, you can know this. The closer you are to 0, the eccentricity, I should say, is to 0, the closer that ellipse is going to be to a circle. So a circle actually has eccentricity exactly of 0. An ellipse is always between 0 and 1. The closer it is to 1, the more elongated that ellipse would look. The closer it is to 0, the more circular it would look. All right, we have the same instructions on this next one. Let's work on it. Now we do, as you can see probably right away, we have some new things to deal with. For one, we have a center that's moved off the origin. It's at 1 and -3 this time. I probably should point out, I didn't write it or say it, but I noticed right away with a 9 and a 7 here, this is definitely an ellipse. Okay, so we found the center. Radius doesn't apply. We're going to need to find vertices, foci, eccentricity, and sketch the graph. All right, our a squared term is 9, so that means a is equal to 3. Our b squared term is 7. That means b would be the square root of 7. We might as well go ahead and find c. So we know c squared is equal to a squared minus b squared. So c is going to be the square root of 2. Once we put this information together, honestly, we have enough to be able to start sketching the graph. So I'm going to start by marking the center. It's at 1 and -3. I know that the larger of the two changes, the a value, is horizontal, so I'm going to mark 3 spaces right and 1, 2, 3 spaces left. I know that vertically we're changing by square root of 7. Now, square root of 7 is approximate, of course, but it's between 2 and 3. I'm just going to mark it somewhere in between 2 and 3. We're not going to get too crazy about the precision on marking square root of 7 on an elliptical graph. All right, so I have enough to be able to sort of sketch an ellipse that looks somewhat elliptical. All right, we'll roll with it. Okay, I need to mark some of the key information. Now, here's the thing to remember. The center's at 1, -3. The vertices were to the left and right of that center. Okay, so I don't actually have to write the 2 points out separately. If you'd like to, you could do it like this. The vertices are 1 ± 3, -3. Now, of course, that's the same as saying 4, 3, or 4, -3, excuse me, and -2, -3. You can do it that way too. We haven't talked about where the foci are. I'm going to change colors here so we can see those. They're the square root of 2 away from the center, which square root of 2 is about 1.4, so I'm going to mark those there. The foci are at 1 ± square root of 2 and -3 still. And then lastly, we need to talk about the eccentricity. The eccentricity here, it's always c over a, so in this case that's square root of 2 over 3. Now if we're approximating that value, it's about 0.47. Now my drawing may not be the best way to look at this, but if we sketched this on using technology, or if you were better at drawing the ellipse than I was, you might notice that this one looks somewhat circular. So even at an eccentricity of, we'll call it a half, about a half, we're already getting a little bit closer to looking like we have a circle. All right, same instructions on this one, but this one's going to be pretty fast. You notice that the denominators are both 25. This is a circle, folks. And when it's a circle, we can just start by labeling the center. It's 3, -9, and we know the radius would be 5. All we're really going to have to do at this point is sketch that thing. There's really not much else for us to do. 3, -9, radius is 5. So what I'm going to do is mark the points that are left, right, and above. Now obviously below is going to be a bit of an issue. You could try to approximate if you want, and I'm going to use my little tool so I can draw a circle. It's nice and amazing, just like all my drawings are, except this one's better. Okay, last thing, eccentricity. Well, the eccentricity of any circle, as I mentioned before, is 0. Okay, the number 0 looks like a circle. Therefore, that's not why, but it is. All right, let's take a look at number 4. On this problem, we have the same instructions as what we had before, but you can see we're in a general form here. So we're going to have to do a little bit of work first. So first thing I'm going to do is group the x terms and group the y terms, because I'm going to have to complete the square. And you know, since I'm going to complete the square, I might as well start by doing this. I'm going to have x squared minus 6x. I'm factoring out the 9, and I'm going to leave myself a little space. And then I'm going to do plus 4 times y squared plus 10y, and I'm going to leave a little more space. And I know this is going to be -37, and then I'm going to have to add some numbers. All right, so what I'm going to do to complete the square right here, that's going to be plus 3 squared, which is 9. But remember, it's not just 9, it's 9 times 9. So I'm adding 81 over there to balance that. For this particular term, I'm adding 5 squared to complete the square, which is of course 25. But again, you have to remember, I'm not just adding 25, I'm adding 4 times 25. So that would be plus 100. And then we can work on cleaning this up. So here we go, we'll have 9 times x minus 3 squared plus 4 times y plus 5 squared equals 144. Now, in order to get this to look like the standard form, what we need to do is divide both sides of the equation by 144. And this one works out nice and clean for us. So we'll have x minus 3 quantity squared over 16 plus y plus 5 squared over 36 equals 1. All right, let's start listing off the key information. The center we know would be 3 and negative 5. The a value is the square root of 36, so it's 6. And the b value is the square root of 16, or 4. C squared would be a squared minus b squared, so c is the square root of 20. I'm just going to leave it at square root of 20, I think. I mean, if you want to change it to 2 square root of 5, that's fine. But I'm going to just do square root of 20 for our purposes here. Okay, I think we're ready to sketch. Let's do that. So 3 and negative 5 would be our center. Our a term is 6, and remember the larger number is connected with the vertical portion here, so I'm going to move up 6 and down 6. Yep, off the grid again. That's all right, we can live with it. And then the horizontal is connected with the b term, which tells us we got to move 4 spaces in those directions, and then we can go ahead and sketch. All right, there's our ellipse. The only thing I don't have on the ellipse would be the foci. I'm going to go ahead and put those. It's square root of 20. The reason I went ahead and left it is square root of 20 is because it's easy for me to look at square root of 20 and say, well, that's between 4 and 5. So 1, 2, 3, 4. I'm just going to mark it in between 4 and 5. If you wanted to be more precise, you could. You could get a decimal, but in the end, it's not really going to make too much difference. All right, so that's what our graph looks like. Let's go ahead and mark down all the key information. We already marked the center. So the vertices, we know from that center we're moving up and down, so that would be 3 and then negative 5 plus or minus 6. It didn't ask us for co-vertices, but those would be 3 plus or minus 4 and negative 5. I'm not going to list them though, but I am going to list the foci. And the foci, again, move vertically, but instead of moving 6 spaces, they move square root of 20 spaces. And then the final thing we need to deal with is the eccentricity. That's c over a, always is c over a, which in this case would be square root of 20 over 6. And that is approximately 0.75. All right, let's move on. I'm going to move through number 5 fairly quickly for a couple reasons, primarily because we just did a problem very similar to this. So I'm not trying to lose you. I don't think I will, but I am going to move a little quickly. So I'm starting the same way I started the last time. I'm grouping the x terms together, and I'm going to leave a little space because I need to complete the square. I'm also grouping the y terms together, and again leaving some space. I'm moving that constant term over to the other side. Over here it's plus 2 squared. Over here it's plus 1 squared. This one is 4 times 16, so that's plus 64. This one is 1 times 16, so it's plus 16. So this is 16 times x minus 2 squared plus 16 times y plus 1 squared equals 9 plus 16, or simply 25. All right, now again, we need to do some division here. Now, it is a little tricky on, which way you want to do the division on this, but I hope that right now you're looking at this and saying, hey, you know what, this is going to be a circle because it's going to be 16 over 25 and 16 over 25 circle. So I would actually think rather than going to the conic form of an ellipse, what if we go to the conic form of a circle and just divide both sides by 16 instead of dividing both sides by 25. Again, you can do it the other way, but then you're going to have a fraction on a fraction in your denominator, and it just gets a little funny, and sometimes people get confused on which way it needs to be because 25 sixteenths in the denominator just looks a little funny. All right, so here we go. We know the center is at 2 and -1. We know the radius is 5/4, not a big radius. We could also do the eccentricity while we're at it. Because it's a circle, that eccentricity is a whole lot of nothing. All right, so the center's at 2, -1, radius 5/4. This is going to be a pretty small circle, obviously. We're just approximating 1 1/4 spaces in the 4 directions, and I'm drawing that circle by hand. I should have used my nice little tool, but I didn't. So I'm going to move on and call it good. All right. Finally, some clue questions where we're going to work in the opposite direction of what we've been doing. So instead of finding out all the stuff, we're going to find the equation. So we have to think about what do we have to know. So you have to think about the standard form, and if it's vertical, of course, for any ellipse, it's x minus h squared over well, if it's vertical, this would be a b squared plus y minus k squared over a squared equals 1. Sorry for that handwriting, but you've got it written in your notes already. But when you look at this, basically what I need to know is I need to know the center. So on number 6, that center's at the origin. I need to know A and I need to know B. Well, A is the further distance from the center, so that would be 5. The shorter distance would be 4, and that's the B term. I'm honestly ready to roll here because the center at the origin makes this problem easier, honestly. So x squared, that's the horizontal movement. So this is x squared over 16 plus y squared over 25 equal to 1. It's that simple, kids. All right, here's our next one. Now this one, we have to do, 5% more work because I have to be able to think and I have to understand and not memorize the middle or midpoint formula, but I have to be able to think. So here's what's halfway between -8, 2, and 0, 2. That, of course, is -4 and 2. There's your center. Okay, so if you want to draw it in there, you can, but you've got to think about this in terms of, well, what are my other values? Well, the A value, that's 4 spaces away. That's half the length of the major axis. The B value, well, the minor axis has a length of 6, so that value is 3. Sorry, there we go, 3. And this one's horizontal, so I know the larger value is going to be under H, or excuse me, under X. Let's try that again. All right, so here we go. X plus 4, quantity squared. I'll leave the denominator blank for a minute. This is usually how I do this. Y minus 2, quantity squared over something equals 1. We already talked about it. The A term is connected with the horizontal, so 16 needs to go under X, and the vertical aspect is the B term, so it goes under Y. All right, 4 clue problems left. They all have a little bit different information. Let's take a look at them. Number 8, vertices at 0 plus or minus 6 tells me a couple of things. First, I know that the center would be at the origin. Second, I'd know the A value is 6. Okay. Oh, one more thing. If the vertices are at 0 and plus or minus 6, I also know that this ellipse has to be vertical. And by vertical, I mean a vertical major axis. Okay, so it's taller than it is wide. Okay, the foci being at 1, 0 plus or minus 1, I should say, tells me the C value. Now, by knowing A and C, and knowing that A squared is equal to B squared plus C squared, I can pretty quickly figure out that b squared is 35. And yeah, you could figure out b if you wanted, but here's the reality. All it says is find the standard form. So if we're being honest, we don't really care that much about b. We care a whole lot about b squared, right? All right, so I just wrote it this way. I included my center. It's at the origin. The only thing I have left to do is plug in the a squared value and the b squared value. Well, this is vertical, we said. A is connected to the y, so there it is, 36. And then the b value of, or b squared value, I should say, of 35 would be connected to the horizontal part. All right, next one. Again, if you just look at something like knowing the foci, you can figure out a lot. Like, I know right away that if the foci are at 0, 0, and 4, 0, I know the center's at 2, 0. I know that the C value is 2. Also, if it's 0, 0, and 4, 0 for the foci, I know that this ellipse is going to be horizontal. Okay, major axis length of 8, that gives me the A value of 4. And then if we do 4 squared is equal to 2 squared plus b squared, we can pretty quickly figure out that b squared is equal to 12. Hey folks, we're ready to set this thing up. I usually like, again, just to start by marking the center and leaving denominators blank just momentarily, because it's always going to be like that, right? The center is 2, 0, so it's x minus 2 squared plus y squared. Now let's talk about denominators. We said this is horizontal, so the larger value, the a value, should be connected to x. And if a is 4, then this is 16. This is 12. And what we have there, folks, is a lovely standard form ellipse equation. All right, let's do number 10. Again, if you look at vertices, you can figure a lot out. I know the center is going to be at 3, and oh man, this isn't fair. Oh, negative 6. It's fine. What's halfway between negative 1 and negative 11? Add them together, divide by 2 if you need to. All right. Also from that, I can figure out that the a value here would be 5. I can figure out that if the vertices are 3, negative 1, and 3, negative 11, that this ellipse would have to be vertical. And then, oh, this is weird information they gave us. Eccentricity is 3/5. Now remember, eccentricity is c over a is equal to 3/5. But we know a is 5, right? So that tells me then that c has to be 3. And, you know, if I know c and I know a, I can just say, well, I know the relationship here, 5 squared is equal to b squared plus 3 squared. So I know b is 4, or maybe more pertinent for our purposes here is that b squared is 16. And you know what we are? We are ready to write our standard form elliptical equation. So x minus 3 squared plus, and then we'll have y plus 6 squared equals 1. Let's fill in those denominators. We know it's vertical, so I'm going to the y value, and I'm going to write a squared underneath it, which is 25. And then I'm going to go to the horizontal part and write b squared. And then I'm going to be done with that problem. I'm going to go to the one you've all been looking for, the last one. All right. Again, let's look vertices and get as much information as we can. We know the center would be at 3 and 5. Also, if it's 3, 8 and 3, 2 for vertices, I know for sure that it's a vertical ellipse. And I mean 3, 8 to 3, 2, that's 6 spaces. That's the major axis, so I know A has to be 3. And then it gives me the co-vertices, although it's calling them endpoints of minor axis at 4, 5, and 2, 5. That's kind of a giveaway to say that my B value is 1. And I like this because I've got A, I've got B, and I've got my center. So here we go, x minus 3 squared over something plus y minus 5 squared over something equals 1. Now again, we said this is vertical based on the location of the vertices, or you could look at it based on the minor axis. And if it's vertical, that means the a values connected to y, so that's a squared, which would be 9, and then b squared would be 1. That, folks, is the end of your 9-2 ellipses notes. And know it's been kind of lengthy today, but there's a lot of good stuff going on here. Make sure you learn the patterns and do well. Have a spectacular day.